Like most who've grown up in the early 2000s, I was a really huge fan of the Harry Potter series by J.K. Rowling. And I really wanted to find a way I could teleport matter, levitate matter, but I quickly found out that real-life physics doesn't allow you to do that. So during my late teens, I started taking advanced physics courses. I had a physics teacher who used to love telling me stories about a realm where particles behaved differently depending on whether we observed them or not, the quantum physics realm. So that was the first time that I heard stories that kind of gave me the same feelings that I had when I was reading the Harry Potter books, and I was hooked ever since. So a long time ago, Richard Feynman, a great physicist, made a statement that we need computers operating on quantum physics principles in order to simulate quantum physics. And that started a rapid development in the area of quantum technology. And lots of organizations and research groups began starting to realize quantum technology. And I joined the University of Sussex's Iron Quantum Technology Group as a PhD student in order to try and realize quantum computers. So quantum technology is a really big field, and it consists of things like quantum sensing, which tries to make really highly sensitive detectors using quantum physics, quantum communication, which tries to try and guarantee really secure communication protocols. Quantum computers, however, is what I'll be talking about today. So I recently asked AI to generate an image for me of what it thinks a futuristic human being using a quantum computer looks like. So this is what it thinks a futuristic human being is like, sort of a larger-than-life person that looks like an astronaut doing calculations on a glowing pyramid, which is so bizarre because it kind of gives me a really good perspective on what modern society thinks quantum computers are like. It's sort of like sci-fi, almost fantasy. However, this is actually what quantum computers look like today. So the first image is an example of a superconducting quantum computer. And this is what features on the cover of most magazines because it looks the prettiest. But superconducting quantum computers operate on small electronic circuits. So you've got these electronic circuits that exhibit quantum properties. You've also got photonic-based quantum computers, which operate or try to do computation using little packets of light called photons. And you've got trapped ion quantum computers, which I think is the ugliest. But it's still really cool because we're trying to trap atoms and try and do computation with charged particles, trapped ions, sorry. So it doesn't look like any of these, though, are sustainable in a typical household. You know, you can't buy a quantum computer and put it in your home. First of all, you need a heck of a lot of space. You need industrial levels of air conditioning, and you need the ability to cool down to almost minus 200 degrees Celsius. And I don't think every house can do that. So when will quantum computers be available just generally? Well, I want to take you back to 1943. So the ENIAC, this machine, was the pinnacle of modern human technology. And it did more calculations in the 10 years that it operated than humanity was believed to have done since ever. And it needed a whole team of people working around the clock because it broke every couple of days. And it needed industrial levels of air conditioning. It occupied the whole basement of a school. And it cost the US government over $6 million US. So now you can buy an iPhone 4, which is much cheaper, can completely outperform this in every way, and fits in your pocket. So when can you buy a quantum computer that can fit in your pocket? I don't think anyone can answer that question. I definitely can't answer that question. But what I can tell you today, hopefully, is how a quantum computer might operate and how we're trying to make quantum computers realizable in the near term. So I'll be talking about trapped ion quantum computers because that's the field that I work in, and I think trapped ion quantum computers will definitely realize a computer much sooner rather than later. So before I talk a bit about how a quantum computer might operate, I'd like to talk a little bit about how a normal computer operates, just to give you sort of a distinction between the two. So in a traditional computer, you've got electrical signals called bits, which can occupy either a 1 or a 0. You can think of this as a light switch, an analogy. And a light switch can be either on or off. So the more information you want to encode in a bit, the more bytes you need. So for example, if you go to a store and you buy a phone or a laptop, you know that one that has 30 gigabytes isn't the same as one that has 100 gigabytes. You can store a lot more information in that. A quantum computer operates in a similar sort of principle. So you've got a quantum bit, or a qubit for short. And a qubit you can't just have a 1 and a 0. Well, you can, but you can also have every state in between. So a qubit can hold a lot more information than your normal classical bit. And this already gives quantum computers that edge over a classical one. So not only does it give that edge, it allows us to speed up and store a lot more information. The ability for a qubit to exist in both 1 and 0 at the same time is called superposition, which I think is another cool magical property again. How do we, at the University of Sussex, use trapped ions to create a qubit? Well, first, a trapped ion is isolated on top of microchips like these. So using special lasers, like so, we can guarantee an ion appears exactly where we want it to be at a specific position on the microchip. So when you shine laser beams on an atom, they begin emitting light. And this light that it emits, just like a small star, we can see using special cameras. Very recently, David Nadlinger at the University of Oxford took a picture using any camera you can buy in a shop of an atom. That is a single atom on his experiment levitating in free space. I think it's one of the greatest photos I've ever seen, and it's a really amazing pinnacle of humanity. So as well as trapping atoms, how do we use these atoms in order to perform quantum computation? Well, when you shine a laser on an atom, it emits light. And when it emits light, it's bright. And when you turn off the laser, it's dark. So this bright and these dark states are what we use as our 1 and our 0. And this allows us to create our qubit. Another really important part of computation is the ability to perform logic gates. And logic gates allow you to change a bit from a 1 to a 0. In a similar way, a quantum computer also has logical gates. These are called quantum logic gates. But quantum logic gates operate using entanglement, which I'm sure a lot of people have heard about. And entanglement is this really interesting property that a lot of people find it really hard to understand, and they still do. I definitely don't. But I'm hoping to give a small analogy on what quantum entanglement might entail. So imagine you have two boxes. One is a normal box, and one's an entangled box. They both contain the same number of marbles, black and white marbles. So in the normal box, when you reach in, you can't look inside just yet. When you reach in, there's a random chance that you pick up black or a white marble. For example, if you reach in, you could pick a white marble. There's a 50-50% chance. When you reach in again, there's a 50% chance that you pick up black or a white marble. It could be white. If you reach in again, it could be white, and the next color you reach in for would be black. But in the entangled box case, when you reach in, the first time you reach in, there's a 50-50% chance, again, that you have a black or a white marble. Say you pick out a white marble. Suddenly, all the marbles in the box now know collectively that you've picked a white marble. Because what happens is, the next marble will always be the opposite complementary color. No matter how long you rummage around in the box, you have to pick out the opposite color. That's what it means for all the marbles inside the box to be entangled. So the next marble you pick out will be black, the opposite color, because all the colors are now correlated. If you reach in again and you pick a black marble, what will the next color be? It definitely won't be black. It will be white. So that's an example of, or a small analogy of how entanglement works. So how do we use entanglement in normal quantum computation? Well, if I have the property of entanglement and I have lots of qubits, 5, I can entangle all the qubits, and if I detect the state of 1, then all the others I know the state of. And this automatically gives quantum computers that advantage and that speed up over classical ones, and I can perform algorithms a lot faster. So even though I've talked a bit about some of the analogies between a classical computer and a quantum computer, I want to look back at another TED talk that I was watching and I found really interesting by Shohini Goze, who said that quantum computers and classical computers can't be exactly compared. So even though a lot of people want to know about what is different about quantum computer, it uses fundamentally different quantum physics. So you can't compare a candle to a light bulb. So at the University of Sussex's Iron Quantum Technology Lab, in which I'm a PhD student, some of the ways in which we're trying to solve these problems is, in order to make a quantum computer, you need lots of qubits. You need lots of information and a way to store this information. So using specially made microchips, like you can see here, we can piece together a lot of them and scale up the quantum computer such that we can have, hopefully, billions of qubits and operate them and make much faster quantum computers that can outperform the current computers we have. And you might have seen recently a BBC News article saying revolution in quantum computing, or a really big breakthrough, which I think is a pretty grand title. But some of the cool thing, I think the cool thing that we did there was that we took a qubit, and which we've trapped on one microchip, and we were able to transfer that thousands of times between microchips without losing coherence, so keeping the qubit intact. And I think this is a really cool milestone for quantum computers, and hopefully, with all the bright minds and many people who are working on this, some of the really great people who have led this experiment, Dr. Mariam Akhtar, Falk Bonus, and Raphael Lebrun-Collins, I think we can try and make quantum computers, trapped ion quantum computers, a reality much sooner rather than later. And even though there's a lot of really great people working on this, and there's a very intense race towards quantum computers, I think at the end of the day, I'm really happy to be able to say things like, I have been able to levitate matter, I do teleport matter through space, and this is, yeah, it's just a really cool thing for me to be able to do in the back.